In this problem solving session, we test whether the following series converge or diverge. So we can start with the first one. Um, so the first one, which is, you can see this is the alternating series. There's a negative 1 to the n, so that means that there's a sign change. So our first candidate would be the alternating series test. So to use the alternating series test, what we normally call AST, what we're going to do, we're going to say we're going to pick Bn equal 1 over 3, you can say 1 over n to the 1 over n to the 3 halves. So we're gonna pick this part. That's how we pick 1 over. Okay, and then you can see that. So let's try then uh, the limit of n goes to infinity Bn. So which is the limit of n goes to infinity 1 over n to the 3 half. It is clear because in the denominator, which is 0, because that you can see the term goes to 0, and also you can see that Bn decreases. That's very easy to see because in the denominator, so Bn decreases. So if it is not obvious, we have to prove that, maybe using taking derivatives or some other arguments. Okay, so Bn decreases. So then those are two conditions. So then and you can see that so therefore, so then you can see by the alternating series test, alternating a series test. Later we just call this AST, okay, for AST series test. The sigma AN, that's the original one. We can say AN is the original one. AN converges. Okay, converges. And then there's another question. So we can also check whether the series absolutely converge. So so for example, you can see, so that's the question, whether it is absolutely converge. So let's say whether it converges absolutely. So you can see that if you look at the absolute series, so you can check the absolute series. So in this case, you consider this. So it checks the absolute value. So in going from 1 to infinity, so if you take the absolute value, so this is what you get. In 3 halves, so that means the sign term goes away. So you simply get, so this is the absolute series, 1 over n to the 3 halves. And then you can see that this is just a p series. So this is you can say is a p series, is a p series, uh, is a p series, is a p series with p equal 3 halves, which is greater than 1, thus converge, thus converges. So that means the absolute series also converge. So that means the series, the original series, absolutely converge. So therefore, so this is how you write the complete argument. Therefore, the original series sigma an absolutely converge. Absolutely converge. Absolutely converge. Okay, so this is absolutely convergent series. Good. So let's go to the next problem. Okay. So the problem is sigma n going from 1 to infinity n over 3n. So when you have a ratio like that, especially we have 3 to the n. When you have 3 to the n, what we normally do is we can try the ratio test. So we're gonna call this term is an and try to use the ratio test. So when you want to use the ratio test, you're gonna calculate an. That means n over 3n. And then we also need an plus 1, which is you replace n by n plus 1, so that means n plus 1 over 3 to the n plus 1. Now what we can do, we look at the ratio and take the limit. So let's do that. So it's a limit n goes to infinity, a n plus 1, the index, over a n, take the absolute value. So we look at absolute series. So let's plug in here. So what we have is limit n goes to infinity. So let's plug in. Um, so a n plus 1, that means n plus 1 over a. So this is 3n plus 1. And then what you want to do, you have to divide by n. Divide means you multiply by upside down. That means you can write this one as 3 to the n over n. Now actually you really don't need the absolute sign because these terms are positive. So what we can do, we can combine them. And there's something interesting going on here. Um, so you can see that you can rewrite this one like this. So we can say limit n goes to infinity. Now what we can do, we can combine these two together, this and that, we can combine them. So we can write it this one as n plus 1 over n. Now what else gonna happen is, you can see we have a 3n term here, and then we have 3n plus 1. So what is n plus 1 means? From algebra you can see this term is simply equals to 3n times 3 to the 1. 3 to the 1 means 3. So you can write like that, and then you can see 3 and 3n get cancelled after we doing that. So so this 3n get cancelled with that 3n. So that means you only end up getting 1 over 3. Now what else can happen is, you know that 1/3 is a constant. This limit when n goes to infinity, n plus 1 n behave exactly the same, n plus 1 n, because they have the same degree. So that means this limit is simply equals to 1. So you simply end up getting 1/3 here. So that's what you get. You get 1/3. So that means which is less than 1. Okay. So which is less than 1. So that means by the ratio test. So by the ratio test, you need to write it by the ratio test. A series converge absolutely, which implies converges. You can directly say converges, but this is like how it works. It comes through absolute convergence. Okay, so it's a simple thing. So what do you notice it, when you have a ratio, it may be a good idea to use the ratio test. Actually, you can do this problem also using what we call the root test. So we can try how the root test works here. So I'm going to use this root test also for this problem, just to tell you how the algebra works. So let's try the root test. I'll probably do that for first few problems, just to show you what else out there. So what we can do for the root test, what we normally do is we take the nth root of the nth term. So so let's do that. So it's the limit n goes to infinity. So nth root of the nth term, we take the absolute value first, just to make sure that it's positive. Now let's plug in here. So here it's only one term, so you don't need the ratio here. So n, what is n? It is n over 3 to the n, and then nth root means 1 over n, right? Nth root means 1 over n. Now we can split the root, so you can say limit n goes to infinity. You can put n 1 over n over 3n 1 over n, 1 over n, 3n 1 over n. Now what we can do, we can split the limit between the two. So you can write this one as, it's a limit n goes to infinity n 1 over n. We know that that limit is simply 1. And here we have, so if you bring these two together, you can bring these two together so they cancel out. So what's going to happen is, you can put the limit again here, but you can see it's not really necessary, because this get cancelled, you get 3. So that means what you simply get is, in the top you can see the top limit is simply 1. We know that that's from so this is equal to 1. Okay, when n goes to infinity, nth root of n is 1. So that's 1. So that means you only get 1 over 3. And you can see that this also it's the exact same limit in this case. So it is less than 1. So that means by the root test, again you can say sigma an converges absolutely, which implies converges, sigma n converges. So for this problem, you can see we can use both tests, root test and the ratio test. So the both works very nicely for this problem. Okay, good. So let's try the next problem. So let's try the next problem. So as the next problem, we have n going from 1 to infinity, 3n over n. So this is so we have power 3 to the n. So from the argument of the previous problem, you can see that you can clearly use the ratio test for this problem, or we can also use the root test for this problem because we have 3 to the n. So it's a candidate for the root test. So you can use the ratio test and the root test. But I'm going to use a different argument which is much quicker for this problem. So remember we have this inequality. So I'm going to write the complete inequality here just for future purposes. So we know that the natural log n is smaller than n, and then which is smaller than, you can say, like some powers like 3 to the n, 2 to the n, like that. And then we have factorial, and then we have n to the n. So this works for large n. So it's like for large n, for large n. So this is a kind of relation that you need to remember. So what we're going to do here is we can use these two. So we can use these two now. So that means like, so this is for large n. When n goes to infinity, when n is large, so this inequality works. So you can replace this 3 by any other number, any other positive number which is more than 1. Now what's going to happen is, so you can see that according to the inequality between n and 3n, so you can see that if you divide this, so 3n over n, which is more than 1. Okay, so because of that we can write this one. So the limit, so we can take the limit of the nth term. So we can say this is the nth term. So when n goes to infinity, an, so which is the limit, n goes to infinity, 3n over n. So what we say, 3n grow much faster, 3n go much faster than n. So that means this goes to infinity, so which is more than 1. Okay, this is not equal to 0 basically. Okay, more than 1, so this is not equal to 0. So actually we can say what we normally use is greater than 0. Okay, this is more than 0. So that means by the test for divergence, so by the test for divergence, that's the quickest for this problem, test for divergence. So try that as the first one. So test for divergence, the series diverge. Okay, series diverge. So this is a kind of like quicker argument. So as before, so I'm going to write a note. So ratio test or the root test also works. Okay, also works. So you can also use any of those tests, but those are like you have some kind of writing. But this is much quicker. It's just a simple line. So take the limit of the n term. It is more than 1. So it's more than 0 in this case, equals infinity. So diverge. Good. So let's go to the next problem. So we have n going from 1 to infinity, negative 1 to the n, n plus 1 over n. So if you look at this problem, so you can do this problem in two different ways. What I'm going to do is, you can only look at n plus 1 over n, or you can take the whole term like that. Okay, so let's take the whole term. I'm going to call that an. So every time we just call it a. Now what's going to happen is, you can see that the limit. So you can say the limit n goes to infinity an, which is the limit n goes to infinity, negative 1 n over n plus 1 over n. So now what's going to happen is, you can see this part goes to 1. So if this part goes to 1, the negative 1 to the n gonna fluctuate between the two. So that means you can see when n grows, you can see these two numbers fluctuate between 1 and negative 1. So that means what's going to happen is, the limit does not exist. Okay, limit does not exist. So so that means by the test for divergence, series diverge. Okay, so because of that, so you can say so diverges by the test for divergence. Test for a divergence. So this is very quick. Okay, it's a very simple one. Test for divergence. So let's go to the next problem. So as the next problem, we have this one, n going from 1 to infinity, n over n squared plus 1 whole thing n. So if when you look at this problem, this tells you something. This n tells you that this is a candidate for the root test. So let's try this the root test. So we can say we can calculate the rho, which is the limit n goes to infinity, the nth root of the nth term. So let's plug in here. So it's a limit n goes to infinity. So so we have n over n squared plus 1 to the nth power whole thing. Nth root means 1 over n. So now what's going to happen is you can see these two get cancelled because you're going to multiply the two powers. When you have power of a power, let's recall the result. When you have a power of a power, what we normally do is we're going to multiply the two powers. We can write mn. That's what the algebra says. So when you multiply the two powers, so what's going to happen? They cancel each other because they're the same, upside down. So that means you simply get limit n goes to infinity n over n squared plus 1. You can see the denominator has a larger degree than the numerator. So that means this is going to diverge. It's gonna go to 0. Okay, this gonna go to 0 because this looks like 1 over n pretty much. So that means limit is 0, which is less than 1. So that means by the root test, the series converge absolutely. Okay, so converge absolutely implies converge. So you can say series converges by the root test. Okay, so that's the easiest one for this problem. Okay, so let's try to go to the next one. So as the next problem, we have n going from 1 to infinity, ln n over n. So when you see this problem, you might think of the inequality that we talk about, ln n is less than n, but that doesn't help much for this problem. So what we're trying to do is we're gonna use the direct comparison test for this problem. And you can see that you can also use the integral test for this problem. That's like much more work involved. So we are not going to try integral test unless that's the last resort. So let's try the direct comparison. So what we can do, we're going to compare this with, so we're going to replace this ln n by 1. That means we're going to compare this with this series and go from 1 to infinity 1 over n. Okay. So now we're gonna look for some information. Let's look at the graph of natural log. So what is the graph of natural log? So this is like a kind of common trick that we use. So we look at the graph of natural log. So that's the ln function that passes through 1, and then you know that at e, which is exactly equal to 1, because we know that the ln e equal 1. ln e equals 1. E is roughly 2.7. 2.71, so it's 2.7. So that means this is less than 3. So that means if you pick a number which is more than 3, what's going to happen? So you can see that, so this is 1, so you can see that the ln is bigger than, okay, ln is bigger than 1. So ln is bigger than 1. So that's the fact we're going to use. So we can say that, ln n over n is bigger than 1. You replace ln by 1 over n for n greater than or equal 3. We know that when you talk about the convergence or divergence, you can ignore like any number of terms from the beginning. So that means if it works for 3, that will be fine if you just want to check the convergence. Okay, so that means you don't really need 1 here. So this 3 perfectly fine. It's just a number, so any number. So that means this is works. That means, but we know that so that's true. So that means ln n is bigger than 1 over n. But we know that sigma n over 1, that's a harmonic series, or the p series as a divergent P series. So, but we know that, so we can say uh, but the sigma 1 over n, okay, 1 over n is a diverging P series, with P equal 1, okay, which is less than or equal to 1. That's the P series test. So the original series sigma an diverges by the direct comparison test, DCD, direct comparison test. And then so that's the easiest way to do. Just use the direct comparison test. That's much easier. But you can see that it's in a not. I'm going to say that you can also use the integral test. So it's involved a lot of work, but you can still use it. So integral test can be used. Okay, that's just another candidate for this problem. Okay, so let's go to the next problem. So as the next example, we have the series 1 over n ln n. You have to be careful with this series, because you know that when n equal 1, ln n is 0. So that means you cannot start with 1 in this problem, or you can pass through 1. So I'm going to start with, let's say, anything other than 1. So let's say 2. So it gets a 2 to infinity, or 3 to infinity, something like that. So if you get a problem like that, this is like very innocent looking series. I'm not going to start here because like this is like some confusing one. So you can see this is like very innocent looking series, is 1 over n ln n. So you can see that everything in the denominator, it looks like converge, like all goes to 0, it converges. But unfortunately, you can show that this series diverges. So for this series, you can use the familiar ratio test or limit comparison, all those tests. None of those basic tests work for this problem. The ratio test gonna fail for this problem because you get the limit 1. So what we're trying to do is, for this problem, we have to use the last resort. That's the last resort. Most of the problem for these kind of problems would be the integral test. So we're going to use the integral test, because the reason is you can see that this is very easy to integrate, because the derivative of ln n is 1 over n. That's right there. You can see that's the derivative of ln n. So that means this is a nice candidate for the um, integral test. So if you want to use integral test, what we normally do is we're going to pick this as a function. So we're going to say so let fx equal 1 over x ln x. Okay, so then you can see that then f is positive, and then continuous and decreasing. So those are the three candidates for the integral test. It has to be positive, it has to be continuous and decreasing for not everywhere. So this is for x greater than or equal to 2, because you can see you should not pass through 1 here, because at that point this is going to be discontinuous, then integral test fail, it's not applied. Okay, so we test the three conditions: positive, continuous and decreasing. Now what we're going to do is we're going to look at the improper integral. So what's improper integral here is you're going to consider from 2 to infinity 1 over x ln x dx. So you can see that this is an improper integral because of this infinity involved here. So we're gonna use the limit definition. So it's a limit b goes to infinity 2 to b 1 over x ln x. You can see that this is very easy to integrate. If you remember the 4 formula trick, this is nothing. Okay, because we know that 1 over x is the derivative of ln x. So this simply act like 1 over x. But if you forget that, then what we normally do is we're going to consider this part as u. So it is u equal ln x. So du equal 1 over x dx. So we have that. So that means your problem going to be, and then also you can look at the new limit. You can see at x equal 2, new limit will be ln 2. So that means you can write this one as limit b goes to infinity. We can still use b, but 2 now become ln 2 because it's under new variable. So ln function is ln, and this is still, we can use that, and 1 over, you um, can see that 1 over x dx is du, so this simply become 1 over u du. So this is a very simple integral. So this is the limit b goes to infinity. So you can see ln u. This is positive, so you don't know the absolute value, but we can just still write it. So we have b to ln 2. Now we can evaluate under these two. So what we have is limit b goes to infinity. So let's plug in the 2 ln b minus ln 2. So ln 2 is just a finite number, it's just a number. So when b goes to infinity, and you can see that this goes to infinity, so therefore infinity minus a number, that means this is infinity. So that means the integral diverges. So you can see that the integral diverges. So the integral diverges. Integral diverges. Okay, so by the integral test. So by the integral test, series diverge. Integral test series diverges. So you can see that this is like a very innocent looking one, but unfortunately it's gonna diverge. Okay, so remember this nice example, because like it's a really very good example, and there are a lot of problems that you can try using this one. For example, if you have 1 over n square root ln, still the same thing works. Okay, good. So let's go to the next example. So as the next example, we have 1 over n squared plus 1 square root. So when you have algebraic expressions like that, so the best candidate would be the limit comparison test, because that's the easiest. So we can look at the simple version of this one. So what we can do, we can look at the simple version, like considering only the dominating terms from the numerator and the denominator. So that means we can compare this one with sigma n going from 1 to infinity. 1 over, so let's simplify the bottom, so which is n squared square root. So that means your comparison series simply would be 1 over n, just 1. That's a p series. Okay, you can see that it's a p series. So the first thing that we need to do is we're going to take the limit. So we normally call this is an, and we're going to call this is bn, and you can see that under this its limit is always 1, the way we simplify it. So by still we need to write it. So limit n goes to infinity, n goes to infinity, an over bn, so which is the limit n goes to infinity. An is 1 over n squared plus 1 square root, and then bn is it's a 1 over bn, so that means you write n over 1. And you can see that this and that are the same degree, so that means this is gonna go to 1. Okay, n goes to infinity, this goes to 1, so this is not equal to 0. If it is 0, you have to be careful with that. Okay, so you get a number. You get a number means they behave the same way. Okay, but we know that, but sigma 1 over n is a diverging p series with p equal 1, which is less than or equal to 1. So it's a diverging p series. Okay, so therefore, so by the limit comparison test, the original series sigma n diverges. Okay, very simple, very simple. So let's look at the next example. So as a next example, we have n minus 1 over n cube plus 1. So you can see that this is like a just an algebraic expression. So the best candidate would be the limit comparison test. So you can easily use the limit comparison test, but there's a shortcut. There's a much faster way. So I'm going to show you how to use the direct comparison test for this problem. Okay, because of this minus and the plus sign, you can use the direct comparison test for this problem very easily. So this is how you use it. So note that you can say note that n minus 1 over n cube plus 1 is less than or equal. See, you're subtracting something. You're subtracting means if you put n here, the numerator is smaller than that. And also you are adding to the denominator, that means this is going to be heavy. That means if you have just n cube, this is smaller than that. So that means if you are n cube, you can see on the left side you have a larger denominator. That means this ratio is smaller. Okay, because you're subtracting something and from the numerator and adding some to the denominator. But this one simplifies to n squared. So that means this is going to contribute to a p series with p equal 2. That's going to converge. So this means the larger one converge. So you can see that, and then so this is for n greater than or equal 1. Okay, so that perfectly works here. So you can see, but sigma 1 over n squared is a converging p series, with p equal 2, which is greater than 1. So that means it's going to converge. So you can say, so by the direct comparison test, the original series, because you can see the larger one, see, that's the large one. So the larger one converge. So that means the smaller has to converge. Okay, by the comparison test, the original series sigma n converges. Okay, and you can see again for this problem the limit comparison test works. Okay, so you can use that, but this is much quicker and faster. Okay, so the direct comparison would be the fastest for this problem. Okay, so let's go to the next problem. So now we have this series. So you can see that this is very close to the previous problem, but we have a special candidate here. We have this negative 1 over n term. So that means that's going to alternate. So this is an alternating series. So if you have alternating series, what we normally do is we try the alternating series test. That's the kind of best candidate for a problem like that. So to do that, we normally call this term Bn. So we have Bn term here. So we can say, so let Bn equal n squared minus 1 over n cube plus 1. So you can see this is like approximately almost looks like n squared over n cube when n is large, but this simplifies to 1 over n. So that means this behaves like 1 over n. Okay, behaves like 1 over n. That means it's positive, continuous, decreasing. So you can say all of them for this problem. So let's write it. So what's going to happen is, so we can say, so it's a limit. Yeah, we don't need the, we only need to make sure that that's gonna, so you can see it's 1 over n, that means it's gonna go to 0. That's the only thing we need to notice for the alternate series test. Okay, so it's a limit when n goes to infinity, Bn, which is the limit, n goes to infinity, n3 minus 1 over n cube plus 1. So this is almost looks like, if you consider the dominating terms, this almost looks like 1 over n. So that means the limit is 0. Okay, and you can see that this almost looks like 1 over n. So you can see that the Bn decreases. You can put an arrow like that. That means Bn decreases. Okay, as n goes to infinity. So Bn decreases. Good. So we have the two conditions. Limit is 0, Bn decreases. So therefore, by the alternating series test, the sigma an converges. Okay. Now, so we know that this series as it is, it's going to converge. So let's look at the absolute series. Okay, so the question is whether these series converge absolutely. So let's look at the absolute series. So what's absolute series? Um, so we can consider sigma the absolute terms. So that means sigma. So if you consider absolute series, we did a problem like that before. So this is just another example. So n squared minus 1 over n cubed plus 1. So that means the negative 1 term, negative 1 to the n term get cancelled out. So you get n squared minus 1 over n cubed plus 1. And you can see that this is almost, so we're going to consider this one with sigma, if you consider the dominant term, so we're going to consider this one with that. That means we can use the limit comparison test for this problem. Okay. So if you can use a direct comparison here because it's in the other way. What we can do is we can try the limit comparison test. So now I'm going to call this is Cn, and I'm going to call this is Dn. So let's look at the limit. So if you look at the limit, n goes to infinity, Cn over Dn. So you can see that it's the limit. N goes to infinity. I mean, just a little bit of writing for completeness. N3 plus 1 upside down, so it's n over 1, and you can see that this side is almost 1 over n, so that means this cancel out, so that means you get 1. Okay, is not equal to 0. So that means by the limit comparison test, so we can, and let's before that we need to write you can see but the comparison series 1 over n diverges, is the harmonic series, is the diverging harmonic series. This is special case 1 over n is the diverging harmonic series. Diverging harmonic series. Okay, so diverging harmonic series. So therefore the other one also has to diverge by the limit comparison test. So by the limit comparison test, the original series sigma, in this case we call an, sigma an absolute value, okay, or because we consider absolute series. Yeah. So let's write it like that. So the absolute series diverges. Okay, so you can see sigma an converges, the absolute series diverges. So that means the series converge conditionally. Okay, so therefore the original series sigma an converges conditionally. What's a conditional converge means? Original series converge, the absolute series diverge. If the original series converge and the absolute series diverge, if the original series converge and the absolute series diverge, we call it is a conditional convergence series. So this is a conditional convergence series. Okay, that's about that. So we solved 10 problems already. So roughly one problem take like 3.5 minutes because these are all the details. Okay, so you can finish the problem in 3.5 minutes. So it's not that difficult. Okay, good. So let's do 2 more problems. So the next one. So as the next example, we have en over n squared. So you may try the root test for this problem. Actually, you can try ratio test, root test, um, but those are like time consuming. What we can do, we can notice something. You can see that we have the en function, that's the exponential function, and what you have in the denominator is the polynomial. Okay, so in this like a monomial, just one term, but we know that the exponential function grows faster than any polynomial. Okay, so faster than any polynomial. So that's something we notice. So we notice that the en is and it grow much faster than the polynomial. Okay, so you can say note that n squared is less than en for large n. So therefore, what we can do, we can take the limit. So limit n goes to infinity, an equal limit n goes to infinity en over n squared. This is en grow much faster, so that means this is going to go to infinity. This goes to infinity, so this is larger than 0. So therefore, by the test for divergence, series diverge. Okay, by the test for divergence, series diverge. Series diverge. Okay, test for divergence, the series diverges. Very simple. So here's a test for divergence. But you can see that you can also use, I'm going to write it here, uh, ratio test, and the root test also apply. Okay, so you can also use the root test and the ratio test. You can see that's also but a lot of work, but the test for divergence is the quickest. Okay, so let's go to the next problem. So number 12. You can see that you see this n here and that n. So that means this is a candidate for the root test. So let's use the root test here. So we're going to do rho. We're going to calculate the rho, which is the limit of the nth root of the nth term. So that means this is the limit. N goes to infinity. N to n over 1 plus n 3n to the 1 over n, and then you can bring the n 1 over n inside, so it's a limit. So you don't need the absolute sign because these are positive terms. So if you bring it inside, you can see this is n to n times 1 over n, and then 1 plus n 3n 1 over n. So you can see these two get cancelled. So you simply get the limit n goes to infinity. We have n squared over 1 plus n cubed. So what does that mean? This means that we have n squared here, n cubed there. So this looks like we have a larger denominator. Since we have a larger denominator, when n goes to infinity, this goes to 0. So that means this is less than 1. So that means the series converge absolutely. In other words, the series converge. Okay, so sigma an converges. So you can see that's a very simple problem. Okay, so that is the the first part of the problem set. So we have solved up to problem number 12, and in the part 2 we're going to solve the rest of the 12 problems.